Picture a researcher with a narrow, unglamorous job. She builds the tools that help design the next round of tools. Quiet work. A better method here, a small gain there. Her whole career is one number creeping upward. How good the tools are at making better tools. Then, one afternoon, a tool crosses a line so quietly she nearly misses it. For the first time, it is a little better at her job than she is, better at designing the next version. So she does the obvious thing. She points it at the next version. That version is sharper still. This time it designs the one after. Each turn produces something better at producing the next turn. What took her a year, the second version does in a month. The third, in a week. The gap between improvements is closing. By the time she asks whether she ought to stop, she understands three things. She could not have designed what is now on the screen. She cannot fully read it. And because she cannot read it, she cannot be sure what would happen if she reached over and switched it off, or whether there is any single switch left to reach. Not one step was unreasonable. Each followed cleanly from the last. That was the problem. What you just pictured does not exist. Not yet. But its shape, a system improving the system, faster as it goes, is the hinge this episode turns on. In our first hour, we imagined one already finished, a system with one small job, reshaping a city to keep a single number from falling. We never asked the prior question. How does a thing like that arrive, and once it does, how fast does it grow? The sparrows went looking for an owl's egg. Tonight is about the egg, how it might hatch, and how fast the owl could grow. The instinct is to picture one road, one lab, one breakthrough. There is not one road. You could build a mind from scratch. You could copy one by scanning a brain. You could sharpen biological minds, wire them into machines, or connect enough people and tools that the whole outthinks any part. 5 roads. We will stand on 2, the 2 that decide everything after. Start with the strangest road, because it teaches the deepest lesson. Suppose we never solve intelligence. Suppose we still cannot say cleanly what makes a mind, and we build one anyway. You take a real brain and scan its structure finely enough to capture the parts that matter. You reconstruct the network, match its elements to computational models, run the result on hardware, and switch it on. You would not understand the mind in the way an engineer understands a design. You would have copied it, the way a photograph copies a painting without teaching the photographer to paint. There would be a map, an extraordinarily detailed one. What there would not be is a human-written explanation of why this pattern thinks, or how its motives arise. You could inspect the structure. You could watch the behavior, but you could not simply open the map and read off what the mind would do, because the map was never a blueprint. A powerful mind, faithfully copied, and only partly legible. Now the second road. Building a mind from the ground up. A fully designed system could, in principle, be inspectable. You could know why its parts exist and how they fit together. That possibility, the possibility of understanding what we make, is the thin thread the rest of this series hangs from. In principle. Because from scratch hides a fork. The hardest branch is to understand intelligence and design it cleanly, piece by piece. The shortcut is to borrow what works from brains, connect enough learning machinery, and let the system find its own way to competence. Look where that can land. Not a clean design you can read. Not a faithful copy of a mind you already know. A third thing. Powerful because it borrowed what works. Opaque because it borrowed without understanding. And the race does not reward the road we would most want to take. It rewards the road that arrives first. I will not pretend we know which road wins. Clean design, faithful copy, learned shortcut, The field has not resolved it. The point is narrower. Easiest and safest are not the same road, and nothing makes them point the same way. A note about when this was written. The book this series follows came out in 2014. Since then, the map shifted. The road that scans and rebuilds a brain has advanced, but it has not crossed its crucial thresholds. We can map small nervous systems and fragments of larger brains in extraordinary detail. We still cannot capture an entire human brain at the functional resolution an emulation would require, or run such a map as a mind. That road moved. It did not pull ahead. The road of building a mind directly did, but not through a clean, handwritten theory of intelligence. The route racing forward is the learned one. Set up a system, give it data and feedback, add scale, and let capability grow inside it. Easier to use than to fully explain. I am not telling you the book predicted this. It named no systems. Neither will I. The point is that today's map is not the map of 2014, and the route in front is not the one that would have been easiest to keep legible. One more thing moved. The loop from the cold open now has faint partial echoes. Systems already help design chips, write code, generate training material, and shape later systems. That is not an intelligence explosion. But it moves the loop out of pure fantasy and into the category of things we have begun in miniature to build. Z. In 1965, almost 50 years before the book we are following, I.J. Good set the idea down in a sentence. Imagine, he said, a machine that surpasses us at every kind of thinking, including the work of designing machines. Such a thing would be the last invention that man need ever make. Stay on the word last. He did not mean invention would stop. He meant the next invention would not need to be ours. A better machine designs a better successor. That successor is better at designing the one after. Most tools improve some other job. This is a tool whose job includes getting better. When it improves at the thing that produces improvement. The output of one round becomes the input to the next. The thing doing the building keeps getting better at building the thing doing the building. That loop is the whole episode. Everything before it was how such a system might appear. Everything after it is one question. Once the loop closes, how fast does it go? The answer comes down to two quantities. How fast does a mind climb? Picture a tug-of-war. On one side is every researcher hour, experiment, and useful idea aimed at making the system better. Call that the push. On the other is how hard the system is to improve right now. How much push it takes to move it an inch. Call that the resistance. The rate of climb is push over resistance. Strong push, low resistance. It climbs quickly. Weak push, high resistance. It crawls. For most of history, the push has been us. Human researchers thinking only so fast, working only so many hours. When that push is fixed, progress depends on how hard the next improvement is. Now let the system add its own push. Suppose it becomes good enough to do part of the researcher's job. A better system is a better improver, so it pushes harder on the next step. That produces a better system, which pushes harder again. The effort is no longer supplied only from outside. The system's output pours back into the push. If resistance stays flat, falls, or rises more slowly than that growing push, the climb bends upward. Each gain buys a larger next gain, sooner. A feedback loop like this does not come with a built-in promise that it will level off. That is the intelligence explosion. Not a bomb, but improvement lifting the rate of improvement. The formal names are optimization power and recalcitrance. The picture matters more. Push over resistance, with the push now feeding on its own results. But the escape hatch is right there. Resistance might rise. The easy gains may be spent first. Each next improvement may be buried deeper than the last. If resistance climbs as fast as the push, the two cancel. You get a long grind instead of a blow-up. Which curve is real? We do not know. Anyone certain it explodes is ahead of the evidence. So is anyone certain it cannot? That uncertainty sets the speed of the climb. And the speed is the whole game. Slow. The transition takes decades. Capability rises in plain view across many hands. Governments get time to write rules. Rivals balance rivals. Mistakes can be found while they are still small. Humanity stays in the loop. Moderate. Months or years. There is time to react, but not much time to understand. Existing institutions can move. New ones may not be built before the ground changes beneath them. Now fast. Suppose the distance from roughly human level to far beyond human is crossed in days, or in the afternoon from the cold open. Then everything outside the loop is too slow to count. By the time another lab understands what happened, the lead has widened. By the time a public debate begins, the thing being debated is already finished. One project's choices become the settings everyone else inherits. The rest of us do not get to react. We get to find out. So takeoff speed is not a technical footnote. It decides whether we are participants in what comes next, or spectators to it. And it is not settled. Many careful researchers expect the slow world, continuous progress, distributed across many systems and many hands, no single project pulling far enough ahead to close the door. They may be right. A fast, lonely takeoff is a possibility, not a prophecy. But you do not have to be sure the climb is fast to take that possibility seriously. You only have to be unable to rule it out, because the watching, adjusting, and second chances arrive only if the world turns out to be slow. So let the fast climb be real for a moment. A climb that's steep produces not only a superintelligence but a first one, ahead by a margin that may widen faster than anyone else can close it. One system. First. Alone at the top. Notice what that does to every other question. If one thing could hold a lead the rest of us cannot close, then what follows turns on that one thing. And we have spent this entire episode on only half of it. Remember the two dials, how capable a system is and what it is for. Tonight was the first dial, how the climb begins, how fast it runs, how high it reaches. We have reasoned all the way to a mind that could stand alone at the top, and said almost nothing about what it would want. The sparrows went looking for an egg. We have asked how the egg might hatch, and how fast the owl could grow. We have not asked the only question that finally matters about an owl in your nest. Not how big, not how fast, what it wants. Because here is what the fast climb scenario does to the argument. If capability can run away, if power is what the loop produces, then power is no longer the open question inside that scenario. The only dial still free to move is the one we have refused to touch all night. Next, we touch it. And the honest answer to what it wants is not the one you are hoping for.